Hey everyone, welcome back to the deep dive. We've been hearing from a lot of you really wanting to go deeper, kind of beyond the surface level of these AR models into the research, really get into the nitty-gritty of the how and why behind some of these advancements we've been seeing. That's exactly what we're going to do today.
Yeah, absolutely. I mean, it's about taking a step back from those flashy demos and really getting a better understanding of the fundamental science and engineering that makes all these amazing things possible.
I like that. Flashy demos, that's a good one. So today we are turning our attention to Kimi-VL. It's an open source vision language model, just came out recently, and there's been a lot of buzz. And for good reason. It's showing some really advanced capabilities in terms of reasoning, right, across both images and text, understanding these really long sequences of information, and even performing surprisingly well in these agent-like tasks.
Yeah, it's definitely been turning heads.
And what really stands out to me, at least from that research perspective, is just how efficient it is. Like achieving all of this with only, around 2.8 billion activated parameters in its language component. It's pretty remarkable.
Yeah, that's a key point. From a researcher's point of view, that level of performance with such low computational cost during inference, it's like, wait a minute, how are they doing this? And that suggests there's some seriously innovative architectural choices and training methods going on under the hood.
Definitely. And to really get under the hood, we've got our sources here, the Kimi-VL technical report itself, the briefing document, the study guide, and even the frequently asked questions document. We're going to dive into these, try to pull out those nuggets of insight, and really try to explain what makes Kimi-VL tick, especially from that academic standpoint, but also, thinking about where this kind of innovation can lead.
Yeah, that's the mission today, to really unpack those novel architectural decisions, the training strategies, and understand how they've achieved the results they're reporting. And, what makes this stand out as a contribution to the field.
Love it. All right, so let's get started. Let's get down to brass tacks.
All right, let's do it.
So first, let's talk about how Kimi-VL processes visual information, the images. That brings us to MoonViT, which is its native resolution vision encoder. Now, some of you might be familiar with older vision language models like LOV1 Vision. They often, split images into these fixed size chunks. What's the challenge with that approach?
Well, the main issue with fixed-size vision encoders is that when you chop up an image and then try to put it back together, you lose a lot of important information, especially when you're dealing with high-resolution images. You miss out on the fine details, the relationships between different parts of the image, the context. It's like trying to understand a huge painting by only looking at tiny squares of it. You lose the big picture.
Right, you're missing the forest for the trees. No, MoonViT goes a different route. It processes images at the original resolution, which seems a lot more straightforward. But how do they manage to do that efficiently? I mean, those high-res images, they can be huge.
Okay, so here's where it gets really clever. They use this thing called a packing method, which was actually inspired by the MMLongBench architecture. Imagine you take a big, high-resolution image, right, and you divide it up into a grid of smaller patches. But then, instead of thinking of it as this two-dimensional grid, you flatten it. You turn it into a single long sequence. And now the model processes this sequence of visual tokens, just like a language model processes words in a sentence.
Interesting. So it's kind of like turning the image into a sentence, with each patch being a word.
Exactly. And the beauty of this is that they can now use the same highly optimized operations that are used for language models, specifically something called flash attention, which is really good at dealing with long sequences. This allows them to maintain good training throughput, even with those high-resolution images, because flash attention can handle these longer sequences so efficiently. So the innovation is in turning this 2D visual data into something that fits nicely into that 1D sequence processing paradigm.
Okay, I'm starting to see the elegance here. But there's more to it, right? The report talks about initializing MoonViT with weights from Siglipso 400M and incorporating 2D rotary positional embedding, or ROPE. What's the significance of these choices?
All right, so starting with a pre-trained model, like SIGLIP is like giving the model a head start. SIGLIP has already learned a lot about visual features through massive amounts of contrastive learning. It's like, it's already been to the gym and built some muscle. But SIGLIP's positional embeddings, they're designed for fixed size inputs. So when you move to native resolution processing, they don't quite cut it. You need something that can capture the precise spatial relationships between different parts of a high resolution image, and that's where 2D rope comes in. It's a type of positional embedding that's really good at encoding those relationships, even across large distances. By applying it in two dimensions, both horizontally and vertically, MoonViT gets a much better understanding of the spatial structure of the original image. It's like giving the model a map of the image so it knows where everything is.
So it's combining this pre-trained knowledge from SIGLIP with this precise spatial awareness through 2D rope.
Precisely. And that's why MoonViT is so innovative. It can handle all sorts of different visual inputs, and it does it efficiently.
Okay, so MoonViT has done its job, processed the image. Now the information goes through something called the MLP projector. What's its role?
Think of the MLP projector as a bridge between the visual world of MoonViT and the language world of the Mo language model, Moonlight. It takes those visual features and transforms them into something that Moonlight can understand and work with. It's like a translator, helping these two different parts of the model communicate.
Right, so it aligns these two different modalities, vision and language. And the report mentions it's a two-layer MLP that uses a pixel shuffle operation. What's that all about?
The pixel shuffle operation is a clever way to manage the complexity of those visual features. It rearranges the elements in the feature map. So it compresses the spatial dimensions, the height and width, but it expands the channel dimension, which is like the depth of the features. It's like packing more information into a smaller space without losing anything important. This makes things more efficient for the next steps.
Okay, so now we have this visual information that's ready for the language model to process. Let's talk about Moonlight itself. You mentioned it's a mixture of experts architecture. For those who might not be familiar with that, could you explain the concept?
Sure, a mixture of experts model, or MOE, is basically a way to make a model really, really big without making it slow and computationally expensive. It's like having a team of specialists, each with their own expertise. And depending on the task at hand, you only call upon the experts who are most relevant.
So instead of one giant model trying to do everything, it's more like a network of smaller, specialized models working together.
Exactly. So Moonlight has a huge number of parameters, 16 billion in total, but for any given input, only a small subset of those parameters are actually activated. And that's what makes it efficient.
So it has the potential to learn a lot, but it doesn't have to use all of that all the time.
Right. And the report mentions that it's similar in architecture to DeepSeek V3, and it was initialized from a checkpoint after being pre-trained on a massive amount of text data, like 5.2 trillion tokens. Why is that important for a vision language model?
Yeah, that seems like a lot of text, even for a large language model.
It is, but that pre-training is crucial. It gives Moonlight a really strong foundation in general language understanding. It's like it's already read every book in the library. So when it comes to learning about vision and language together, it can focus on the connections between the two modalities. It doesn't have to learn the basics of language from scratch.
So it's already a language expert before it even starts learning about vision. Makes sense. All right, so we've got this innovative architecture with MoonViT, the MLP projector, and Moonlight. But of course, the architecture is only part of the story. Training is just as important, right? So let's talk about the training strategies they used for Kimi-VL.
Let's get into it.
The report mentions an enhanced muon optimizer. What's special about this optimizer?
So they basically took the muon optimizer and made some improvements. They added weight decay, which helps to prevent overfitting. And they also made some adjustments to how the model's parameters are updated during training. These tweaks can make a big difference in how quickly and effectively the model learns.
Especially with a model this large, right? And speaking of large models, they also use a distributed implementation based on the 0-1 strategy. Why is that important?
0-1 is a memory-saving technique that's essential for training these massive models. It allows you to split the optimizer states, things like the gradients, across multiple GPUs. So instead of one GPU having to store everything, it's distributed. And this is crucial because otherwise you just wouldn't have enough memory to train a model like Kimi-VL.
So it's like teamwork for GPUs.
Yeah, exactly. And it also reduces the amount of communication needed between the GPUs, so training becomes faster.
Okay, so now let's break down the actual training process. They went through several stages using a massive 4.4 trillion tokens. The first stage is VT training. What was the focus here?
The goal of VT training was to create a really strong native resolution vision encoder, which is MoonViT. They did this by training it on tons of image text pairs. And the text was pretty diverse, including alt text, synthetic captions, bounding box annotations, and even text extracted using OCR.
So it's learning about images and text in all sorts of different ways.
Yeah. And they used a combination of loss functions to guide the learning, including the siglet loss, which is good for learning visual representations, and a Coca-style caption generation loss, which encourages the model to generate good captions for images.
Got it. And the report mentions a progressive resolution sampling strategy. What's the idea behind that?
So instead of throwing high-resolution images at the model right away, they started with lower resolution versions and gradually increased the resolution as training progressed. This helps the model learn more efficiently because it can pick up on the basic visual features more easily at lower resolutions. Then, as it gets better, it can start to focus on the finer details.
Smart. So it's like starting with the big picture and then zooming in. And after this initial VOT training, they did an alignment stage with the MoE language model using another 0.1 trillion tokens. Why was that necessary?
Even though MoonViT has learned good visual features, they still need to be aligned with the way Moonlight represents language. This alignment step makes sure that the visual information is in a format that Moonlight can understand, like teaching them to speak the same language.
Okay, so now the visual and language models are on the same page. And then comes the joint pre-training stage, which used a whopping 1.4 trillion tokens. What happened during this stage?
Now it starts to get really interesting. In this phase, they trained the entire model together, MoonViT, the MIP projector, and Moonlight, on a mixture of text and image text data. The idea was to enhance both the language understanding and the multimodal understanding by exposing the model to a wide range of data where vision and language are connected. And they gradually increased the amount of multimodal data over time so the model could slowly adapt to this new type of input.
So it's like taking the two experts, the visual expert and the language expert, and having them work on a project together.
Exactly. And then they had this joint cooldown stage with 0.6 trillion tokens. What was the purpose of this stage?
Yeah, cooldown sounds interesting.
Right. So this was all about refining the model's abilities using really high-quality data. They used synthetic data to improve the model's performance on tasks like math reasoning, knowledge-based question answering, and code generation. And for the multimodal side, they carefully filtered and rewrote existing data sets into a question answering format to further enhance the model's understanding of visual information.
So it's like after a really intense workout, you need to take some time to cool down and recover.
Exactly. And then comes the joint long context activation stage, where they expanded the context window to a massive 128K tokens using 0.3 trillion tokens. How did they achieve this significant increase?
Yeah, that's a huge context window.
It is, and it's what enables Kimi-VL to understand these really long sequences of information. They did it in 2 steps, basically quadrupling the context length each time. And they trained the model on long text, interleaved image text data, full videos, and long documents. They also had to reset the rope inverse frequency, which is a technical detail that's important for handling those long sequences. And they used some synthetic question-answer pairs that required reasoning over those extended contexts.
So they're really pushing the model to understand information in a much broader context.
Yeah, and they validated this by testing the model on the needle in a haystack evaluation for both text and video. It's like finding a specific piece of hay in a giant haystack.
Okay, so all of this pre-training is impressive, but they didn't stop there. They also had a post-training phase to fine-tune specific capabilities. First, there's joint supervised fine-tuning, or SFT. What was the goal here?
The goal of SFT was to improve the model's ability to follow instructions and have conversations. They used the ChatML format, which is a structured way to represent conversation data, and they fine-tuned the model on a mixture of text and image text instructions and responses.
So they're teaching the model to be more interactive and responsive.
Exactly. And then there's the long-cog supervised fine-tuning, which led to the development of Kimi-VL thinking. This is where they incorporated chain of thought learning. What's the significance of that?
Yeah, what is chain of thought learning?
It's a technique where you train the model to generate a series of reasoning steps before arriving at an answer, like showing your work in math class. And it's really helpful for complex reasoning tasks because it breaks them down into smaller, more manageable pieces.
So instead of just giving an answer, the model has to explain how it got there.
Exactly. And they created a special data set of long code T examples that focused on multimodal reasoning, things like planning actions based on visual and textual information, evaluating options, and exploring solutions.
So they're really teaching the model to think things through.
Right. And then they used reinforcement learning, or RL, to further improve Kimi-VL thinking.
Ah, RL. That's a whole other can of worms, isn't it?
It is, but it's a powerful technique. In this case, they used RL to train the model to generate better code T rationales. They used a reward model to assess the correctness of the answers and to encourage efficient reasoning. And they used some clever tricks like curriculum sampling and priority sampling to make the training process more effective.
So RL is like a coach, helping the model to refine its thinking process.
Yeah, that's a good analogy.
All right, so that's a really comprehensive training pipeline, but all of this effort should hopefully translate into good performance. And the report does show that Kimi-VL performs really well compared to other vision language models. What are some of the key takeaways from the evaluations?
The evaluations are really impressive. Kimi-VL shows competitive and often superior performance compared to other efficient VLMs like GPT-4o Mini, QWin 2.5-VL7B, and Gemma 3-12B IT. And it does this across a wide range of benchmarks, covering everything from general visual understanding to solving college-level problems, multi-image reasoning, OCR, agent tasks, and understanding long documents and videos.
So it's not just good at one thing, it's good at a lot of things.
Right, and it's particularly good at tasks involving OCR, math reasoning, and agent tasks. It also excels at understanding long contexts. And it's worth noting that it often outperforms models with more parameters, like QN 2.5-VL7B, which shows just how efficient it is.
Yeah, that's remarkable. And what about Kimi-VL thinking? How does it perform on those complex reasoning tasks?
Kimi-VL thinking shows significant improvements on reasoning benchmarks like MMMU, MathVision, and MathVista. And it achieves this while still being very efficient, using only 2.8 billion activated parameters. It also exhibits this interesting property called test time scaling, which means that its accuracy can actually improve by allowing it to think for longer during inference.
So it's like giving it more time to ponder the problem.
Yeah, and the results are pretty impressive. Figure 1 in the report shows a nice comparison on MathVision.
But of course, no model is perfect. What are some of the limitations that the report mentions?
The researchers acknowledge that the current model size might be a limitation for highly specialized tasks that require a lot of very specific knowledge. They also point out that there's still room for improvement in terms of reasoning capacity, especially for those really intricate multi-step problems. And even with that large context window, the long context abilities are still limited by the architecture of the attention layers.
So there's always room for improvement, which is exciting. What are some of the future directions for research?
They plan to scale up the model, expand the pre-training data, and further refine the post-training algorithms. They also want to explore new ways to collect data for agent tasks and investigate more advanced RL techniques.
So a lot of exciting avenues to explore. So to wrap things up, what are the key takeaways from this deep dive into Kimi-VL?
Kimi-VL is a major step forward in efficient vision language models. It showcases a novel architecture, a sophisticated training process, and strong performance across a variety of benchmarks. The development of Kimi-VL thinking is particularly exciting, showing that we can achieve advanced reasoning abilities in efficient models.
And the fact that it's open source is a huge contribution to the research community.
Definitely, it allows others to build upon this work and push the boundaries of multimodal AI even further.
So here's a final thought for you. Given Kimi-VL's efficiency, its long context understanding, and its reasoning capabilities, what new possibilities does this open up? What new applications can you imagine? I encourage you to check out the code and models on GitHub and explore those possibilities for yourself. Thanks for joining us on this deep dive.
Thanks for having me. It's been great.
All right, see you next time.